Staring at a ceiling. Ooh, look at that light up there. So bright, so beautiful. Well, guys, we're talking about the refraction of light. You see that? Ooh, ooh. Look at them green dots. Them green dots. The reflection.
Guys in my bathroom, you know what I'm saying? So we'll talk about, we'll first talk about reflection. Woo, look at that light. Oh my goodness. You see, this light right here is reflecting off that mirror. And basically, the reflection of light is when light bounces off a surface and it reflects back. You see? Mm-hmm. Boop, 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 boop.
There are two types of reflections. The first type is specular reflection as shown in A and C. This type of reflection is when light bounces onto an object and reflects back at the same angle it hits. This type of reflection only happens on smooth surfaces. The second type of reflection are diffuse reflections. Diffuse reflections are when the object's light hits a surface and bounces back in different angles, as shown in B and D. As you can see in this figure, as the light reflects off this surface, the angle that it hits the surface with is the same angle that it leaves with. This goes into our next basic equation, which is,
As we can see with this lovely equation right here, we see that the initial angle that the light hits the surface with is same as the same angle that it leaves the surface with. Therefore, they're equal in a reflection.
The next thing that we will talk about is refraction. What better to help me with that than some juice? Juice. As we hold this juice up to this lovely shutter, we see that the shutter is not as it appears. Then we look at it by ourselves. See, as the light goes through the juice, it bends. The shutter is not as it seems. And that, my friends, is the lovely effect of refraction. Refraction is the bending of light from the first medium to the second medium with respect to the angle and the normal. As we can see here, as light enters this water, it bends with respect to this normal at an angle theta. Next thing we're talking about is the angle of refraction. Yay! The angle of refraction right here is that what theta 1 goes to theta 2. As we see, when it hits the glass, it bends and goes towards this normal, which is this reference for which the angle refracts or reflects on. So as we see, there is a constant relationship between theta 1 and theta 2, the velocity and velocity 2. That's why they're constant. As the velocity on the outside, before in the air, is greater than the velocity when it hits the glass. So that's why the angle gets smaller, more towards the normal. Because as this is greater and hits this glass, it slows down, causing it to bend and get a smaller angle.
experiments shown that the path of light ray through a refracting surface is reversible. This says that as light moves from a refracting surface, as from air to the glass, it's also the same as moves from glass to the air. As we can see, we have the velocity entering, the velocity refracted, call that V2, velocity refracted, and the velocity leaving. Now, as you can see here, the velocity entering is going to be way bigger than the velocity leaving. That means that the angle entering has to be greater than the angle leaving. It's all with respect to the normal. As we go down here, the angle leaving is less than the angle refracted, all respect to the normal. This is because as it leaves, it gains speed It's going from one medium 1 to medium 2. So the light leaving is the same as the light refracting, as in the top, as is the light refracting is the same as light leaving. They're both the same. When light passes from one transparent media to another, it is refracted because the speed of light is different in the two media. The index of refraction is defined as the speed of light in a vacuum over the speed of light in a medium. Saying N is equal to C over V. This dimensions this number N, the index of refraction, is always greater than or equal to 1 because C is always greater than V. This lovely equation was derived by Snell. One key thing to know is that the frequency does not change. As the light wave gets refracted and moves from one medium to the next medium, through the barrier, the wavelength may change and the speed may change, but the frequency does not change. As we can see in the picture, as light wave moves from A to B, the wavelength gets smaller, and you can see this decrease in speed. But the frequency from trough to crest and crest to trough does not change. The relationship phi equals f lambda must be true in both media, as f1 is equal to f2, which is equal to f. All the frequencies are the same; they don't change. This means the velocity in the first ray of light is equal to the frequency times that first wavelength. Then, as it gets refracted, the second velocity is equal to that same frequency times a different wavelength. In this case, it would be smaller as it's being refracted. This principle with the index of refraction, we get lambda 1 times n1 is equal to lambda 2 times n2. This is saying that the first wavelength before refraction times the first index of refraction is equal to the second wavelength times the second index of refraction. There's a constant ratio between the two. What we'll cover today is Snell's law. Snell's law basically says that as light waves bend as they come in contact with a material, how much they bend is dependent on the initial index of refraction n1 times the angle which they hit the material in, sine theta 1. This is parallel to when it is refracted into and the angle at which it's refracted, sine theta 2. Remember that the angle at which an object is refracted is mostly dependent upon the speed at which the object hits the material. If an object at a high speed hits a material, the angle of refraction will be closer towards the normal. Vice versa, if an object goes at a low speed, exiting the material, then it will have a high speed with the angle of refraction farther away from the normal. Refraction can be used in optical tweezers. Optical tweezers are a scientific instrument that use a highly focused laser beam to produce a force which is due to refractive index difference between the object and the surrounding medium to physically hold and move microscopic dielectric objects. Remember, the refractive index is the ratio between the speed of light and the vacuum relative to the speed in the given medium. Dielectric is an insulator that is capable of maintaining an electric field. That's another chapter that has nothing to do with this. Also, the optical tweezers are also used to trap the dielectric spheres of bacteria, viruses, cells, and organelles and strands of DNA. They track their movements and the small forces, and also altering structures in the body. Reflection are used everywhere. You see them in mirrors. Drivers use them in the rearview mirrors, side view mirrors. The teenage girl uses them when she's doing her makeup every 5 times a day. Ha ha ha. No, that doesn't happen. Maybe, but anyway. Also, doctors use them with the endoscope to see down your throat as the light is shined through the endoscope. The lens in the endoscope is it bends reflects the light off the back of your esophagus and sees in your stomach. Also, dentists use reflective tools. I don't know the name of them.
to use inside the mouth to see around your mouth without having to bend their head sideways and see any cavities or abnormalities in your mouth. And also, reflection is used in concave and convex lenses, as the light uh, is uh, is reflected through both lenses. One of the light is reflected inwards or outwards that the eye sees, and that's it. Yeah, guys, that's all there is to it. To reflection and the refraction of light. If you have any questions, go search the internet and ask Coach Rice. He has his videos on this. And yep. Peace.
Got him.